Hello everyone, today I will be presenting our paper Computational Simulation of Vibration and Aerodynamic Effects in Wind Energy Turbines and Their Environmental Impact. My name is ATANASOVA and I am PhD student of Faculty of Computer Science and Engineering in Skopje. So we will start this presentation by introducing the case study, and that is the Bajroga wind farm in Kosovo. We will present details regarding this wind farm, operational objectives, and aerodynamical and structural analysis. So the key details regarding this farm are that the wind farm became fully functional in 2021 with a total capacity of 105 megawatts and 27 General Electric wind turbines. It is one of the largest wind facilities in Kosovo that is supporting the national transition of sustainable renewable energy system. This study integrates physical measurements with advanced simulation to optimize longevity and power outcome. And that is done through analyzing of atmospheric and turbulence modeling, vibration mitigation, and reliability engineering. So regarding the atmospheric and turbulence modeling, here we use multiple numerical simulation of airflow characteristics and dynamic aerodynamic loading acting of the turbine blades. Regarding the vibration mitigation, we have we are quantifying the turbine blades and the structural vibration responses under varying weather conditions, which means we are doing analyses when we have different weathers, how the vibrations will be affected by that. And regarding the reliability engineering, we are preventing excessive vibration to directly reduce operational downtime, avoid structural wear, and extend component lifespans. All this analysis is done using WaterLink software, which correlates meteorological variables with power outputs, and the parameters that are monitored are the wind speed, the air temperature, atmospheric pressure, relative humidity, solar radiation, and the prescription. So here we will be talking about the primary objective of the wind farm, and that is to maximize the amount of energy harvested from the installed wind turbines. But however, reducing the land area allocated for wind farms in order to accommodate a higher number of turbines leads to decreasing the spacing between them, which has a negative effect of overall energy production. So the wind induced disturbances, particularly turbulent airflow, is commonly referred as something that is called wake effect. This phenomenon represents one of the most significant factors influencing the interaction between neighboring turbines, as it reduces the available wind energy for downstream units and the consequence impact of total power outputs. So Kosovo has committed to achieving 9% of the energy savings that are targeted from the total energy consumptions in accordance to the EU directive. Here the evaluation is executed utilizing the European Wind Atlas model that is implemented, and the inputs that are used are the terrain orography, the surface roughness, and the obstacle exclusion, which means that the terrain orography is detailed digital topographics mapping that are generated specifically for the wind flow modelings. The surface roughness is precise vegetation and land use classification in friction coefficients, and the obstacle exclusion is no significant physical obstacles were recorded here in this part. So the maximum energy production from a wind farm cannot be fully achieved due to the effects described here, and must be therefore carefully considered in wind farm planning, particularly with respect to turbines spacing. So the airflow passing from upstream turbines to downstream units is progressively reduced and becomes increasingly turbulent. So here we have an effect, let's say wake effect consequences. That is a phenomenon that represents a critical design parameter, as it significantly influences the total energy yield of a wind farm. It contributes to variable aerodynamic loading conditions and may induce fatigue-related vibrations to the rotor system and other components. So we have also aerodynamic loading, which contributes to highly variable loading conditions across the rotor plane, introducing structural fatigue. Here we have the wind-induced wake effects and the mathematical modeling. So the turbulence intensity and wind speed are obtained from field measurements, while propagation is estimated indirectly. So we are using a few approaches here, and those are the Kolmogorov approach and the Jensen model. So for the high frequency measurements, the turbulent distribution can be categorized using the subrate approach described by Kolmogorov, and here we have the mathematical formula that he is presenting. And the wake structure of wind turbines is described as a downstream velocity deficit characterized by a conical expansion behind the rotor, which is decaying with the more distance that we have. The Jensen model is also widely used because it's very efficient, and is saying that the wake decay coefficient is described in the linear wake expansion. So we also have turbulence impact on the power production and the mechanical loading, which is very understandable. So here these turbulences introduce critical time-dependent fluctuations in both rotor torque and thrust loading, which directly impacts the turbine performances. So we have three, let's say, main key engineering implications, and those are power output variability, structural fatigue accumulation, and lifetime optimization. So regarding the power output variability, since the aerodynamic power is the product of the rotor torque and angular velocity, turbulences cause constant fluctuations in power output and electrical energy generation. The structural fatigue accumulation is presenting the dynamic loads through the blades, acting as the dominant factor, while we have the mechanical loading of the turbines. And the lifetime optimization is the upstream and downstream of the turbulences that are characterized, and it's essential to implement decisions that approach that the turbines target services life will be ensured. So here we have the wind turbulence intensity analysis in the Mitrovica. So these values were evaluated over a period of 1 year using 10 minutes interval data, and only 10 minutes intervals with wind speed exceeding 3 meters per second were utilized for base calculations. We have 4 different heights that were used in this analysis, and that's 80 meters, 50 meters, 40, and 20. And this table in general represents the turbulence intensity at different heights, as we already said, and for different mean wind speeds, which are 5, 10, and 15. So for every height, we can see that the turbulence intensity rises as the wind speed increases. That we can see here in general. So like for every value, the wind speed increases. So for 80 meters, it goes from 10 to 12.88 to 13.97. 50 meters goes from 10.5 to 13.5 and 14.5 and so on. So this indicates that the stronger winds are generally associated with greater turbulence. So the table shows that turbulence intensity generally increases as the measurement height decreases. So for 80 meters we have 10%, let's say. For 50, 10.5, 40, 11.5, 20, 11.9. So that means that the height decreases, but the intensity increases. So this trend is expected because wind is closer to the ground. The one that is closer to the ground is more affected by surface roughness, vegetation, buildings, terrain, and it is creating more turbulent airflow. The maximum recorded turbulence intensity is 15.6% at 20 meters and 10 meters per second. At 15 meters per second, the turbulence at 20 meters decreases slightly to 15.3, suggesting that the turbulence does not always continue increasing at higher wind speeds. So the difference between the highest and the lowest measurements heights become larger as the wind increases. For example, at 5 meters per second, the difference between 80 and 20 is 1.9 percentage points. At 10 meters per second, the difference increases to 2.72. So from these results, we can conclude that the turbulence intensity is influenced by both the wind speed and the measurement height. So higher wind speed generally produces greater turbulence, while lower heights experience more turbulent airflow due to the ground effects. So here in the next few slides, we will have a presentation for all the data that we saw in the table, just in a graphic form. So here we have the graphical relationship between the wind speed standard deviation and the turbulence intensity for a wind speed of 5 meters per second. The blue line indicates the heights that we already mentioned, and the orange one indicates the values for certain heights. So the measurements decrease from 80 to 20 across the 4 observations, and the values increase for each of these values. The largest difference here between the two series that occurs is at the first observation, 80 meters with 10 meters per second, while the cap becomes much smaller with the fourth observation, meaning 20 meters with a value of 11.9. So as the measurement height decreases, the first data exhibits a reduction, while the wind speed remains relatively stable with only a slight increase. So this, as we already said, suggests that the wind condition vary with measurement height, but the measured wind speeds remain within certain operating range, and this is very important for optimizing the turbine placements because measuring the height influences the available wind resource and the energy production. Here we have the same situation, but with the wind speed of 10 meters per second. Again, we have the heights and we have the values that we already mentioned in the previous, when we were explaining the table. And in here we have the representation of the wind speed of 15 meters per. So, based on the results, we can conclude that the findings confirm that this region possesses significant potential for more wind energy development, to reduce some energy production estimates, and to improve the currency of the wind resource assessment. Long-term meteorological measurements should be continued, and with this measuring process, the data will provide more robust basis for future wind farm design optimization and investment planning. So that is all for this presentation, and thank you so much for your attention.